In this video we're going to analyze another current mirror, which is called a current mirror with a beta helper. We're doing this mostly to introduce the idea of a beta helper, which is a trick that shows up all over BJT designs. In order to justify what the beta helper is doing, we're going to do one more error analysis in this video. But remember that I don't think being able to do error analysis is crucial for today's engineers. So I've drawn another current mirror here, and Q3 in this circuit is called a beta helper. It helps source base current for Q1 and Q2 so that IN doesn't see the base current pulled away. You might notice that Q3 looks a bit like an emitter follower, and that's a good observation. It's acting like a voltage buffer, creating a copy of its base voltage here at its emitter. And that in turn makes IN see a much bigger input impedance. That means Q1 is still kind of diode connected, just like in the simple current mirror, but the diode connection is just fancy. It's got this additional transistor in the loop in order to act like a voltage buffer. If you want to try an error calculation, you can pause the video and give this one a shot. It's optional, because I'm not holding your feet to the fire for error calculations, but this one is pretty satisfying and quick. We start our analysis by noting that I out is equal to IC2, which is beta times IB2, because we usually assume everything is operating in forward active in a mirror. The emitter of Q3 provides both base currents to Q1 and Q2. And those base currents are the same because the voltage on the base of Q1 and Q2 is the same. We can also relate those base currents to the base current of Q3 by noting that IE3 is equal to beta plus 1 times IB3. So that's just going from base current to collector current and adding them up per our usual relationships. KCL at the collector of Q1 lets us see that IN is equal to IC1 plus IB3. And we can use substitutions from the second line to express IC1 as beta times IB2, because IB2 is the same as IB1, and IB3 in terms of IB2. So here we replaced IC1 with beta times IB2, replaced IB3 with a relationship derived from these two equalities. We can rearrange that and use our relationship between IC2 and IB2 to write IN terms of I out. And finally, a little more rearranging gives us our error factor, which is about 99.98%. 0.02% is an acceptably low error, and we have our Q3 voltage buffer to thank for it. So thanks, beta helper. Calculating the other current mirror parameters for this current mirror is pretty straightforward. Pause the video and try to find Vin, Vmin, and R out. Vin has increased to 2 VB on for the current mirror with a beta helper because we need to keep both Q1 and Q3 in forward active. So we need a VBE on to climb to this node, and then a second VBE on to climb up to the input node. That's 2 VBE on. Vmin is still VCE sat, because lowering this voltage only really affects Q2, and we just need to make sure that Q2 stays out of saturation. R out is still RO because the output of the emitter follower... R out is still RO because the output of this mirror still sees just RO connected to ground through Q2. We've paid a bit of V in order to have our good error performance in this current mirror, and we've paid a bit of V in to have our good error performance in this current mirror. There are other current mirror designs that try to break that trade-off, but like almost everything in engineering, you don't get something for nothing. You usually pay in one specification in order to improve another. In summary, beta helpers source base current, The beta helper in this current mirror increased V in, so you required a higher input voltage to keep the mirror operating. And current mirrors generally come with design trade-offs.